Okay. Oh yeah, thanks. Welcome everyone to this year's, I guess, the second AI seminar of ISI. So I'm very excited to introduce Professor Greg Durrett from UT Austin. So he's actually assistant professor of computer science over there, where he leads the NLP group. So Greg's research focuses on making natural language processing systems more interpretable, controllable, and generalizable, which spans application domains including question answering, textual reasoning, summarization, and information extraction. And he has received lots of funded projects by the NSF, DARPA, Bloomberg, Amazon, and Salesforce, so on and so forth. And before joining UT Austin, Greg did his PhD at UC Berkeley with Dan Klein. So today, his talk is about why natural language is the right vehicle for complex reasoning. Let's welcome Durrett to give his very exciting talk.
All right, thanks so much. Okay, it all looks good and everything?
Yes.
Okay. Yeah, thanks, Muha, for the nice introduction. And yeah, it's my pleasure to be here. So thanks, everyone, for coming and taking the time away from your NACL drafts if you're working on NACL. So yeah, today I want to talk about complex reasoning in text, and especially why I think natural language is the right vehicle for dealing with it. So what do I mean when I say complex reasoning? Well, a classic example of a reasoning problem in text is textual entailment. So we have a premise like a dog is chasing a cat and a hypothesis like two animals are running. And we want to know whether the hypothesis is entailed by, contradicts, or is neutral with respect to the premise. Okay, so we have data sets and we can pre-train transformer models on them and kind of correctly determine that a dog is chasing a cat entails that two animals are running, but does not entail or contradicts that they're sitting, right? So there's some kind of reasoning happening here in a latent way. If you try a bunch of different examples, you can see that the model is reasonably consistent at saying that, okay, if you're chasing something, you're not running. And if you're chasing, or sorry, if you're chasing something, you are running. If you're chasing something, you're not sitting. Again, kind of probably. But there's plenty of places where these models break down. If you say three animals are running, the model says entailed, but that's actually wrong. And the problem is that when you have a model like a end-to-end pre-trained model that's making a decision in a completely latent way, it's very hard to diagnose problems with it. So for example, one instance of this that we've studied along with some others was multi-hop question answering. So this was a case where we thought that we had models that were kind of able to combine multiple pieces of information, but it turned out they were taking reasoning shortcuts and not doing the kind of reasoning we expected. And the only reason this was really news is because it was so hard to tell what they were doing because it was all late. Okay, so there's lots of ways to improve this. Things like debiasing techniques or ways of avoiding learning dataset artifacts have been proposed, which might be a way to learn more consistent reasoning. But I'm going to argue that that's ultimately kind of doomed to fail. So here's an example of a question from the natural questions data set. What age do you need to be to buy a BB gun? And the model says 18. And this is the gold context that's annotated in Wikipedia that the kind of supervised data says you should answer this question with. In Manitoba, Saskatchewan, Ontario, British Columbia, and Quebec, the minimum age to purchase an airsoft gun is 18. Okay, two things going on here. One is that obviously this is kind of restricted to certain Canadian provinces. So I'll give a shout out to some of my colleagues at UT. I was not involved with this work, but I think it's great. Michael Zhang and Unsel Choi had this paper at EMNLP called Situated QA, where they annotated a data set with spatial and temporal contexts that might change what the answer to a question is. Okay, so but kind of setting that aside, one issue here is the kind of restrictedness of the context. And also, is an airsoft gun the same as a BB gun? Yeah, I spent a little bit of time on Wikipedia, enough to figure out that this is like kind of complicated. And so ultimately, like, I don't want just a single answer to this question. Before I'm going to go out and buy a gun and break the law, I really want to see some kind of justified reasoning for what's going on And I think that as we get into more and more complex reasoning problems, this just gets more and more true. So here's an example of a fact check from PolitiFact about the claim Joe Biden proposed killing over 600,000 jobs in Pennsylvania supported by fracking. Okay, I can just tell you this claim is false. I don't know if you believe me or not. But I think it's much more convincing if we say, okay, well, why is this false? It's because he didn't call for a total ban on fracking, and fewer than that number of jobs would be eliminated if it weren't totally banned. That's the number that would be eliminated if fracking were completely banned. So I think we really need the intermediate conclusions here to be convinced. So let me kind of contrast with this end-to-end latent reasoning approach and kind of wind back the clock in AI a bit. And let's look at theorem provers. So we could apply these to the entailment examples that we had before, where suppose that we could parse each of these into some kind of formal semantic representation. Maybe we could have a collection of rules and use some kind of automated proof system to basically derive the two animals are running logical form from the input, a dog is chasing a cat, and prove an entailment relationship that way. Okay, so the benefit of this is that we're pretty good at doing search in with these kinds of tools, and they can articulate all the intermediate reasoning states along the way. Okay, the problem with this is kind of everything else. You need a semantic formalism that covers everything that you want to represent about this text. You need a you need a parser that can parse into it reliably. And then you need all these rules in the theorem prover, which are like, always have sort of contextual restrictions. And it's just very hard to actually come up with this set of rules from text. So here's what I'm going to talk about in this talk today is an intermediate middle ground that is going to try to emulate the same kind of idea as theorem provers, but do reasoning directly in natural language. So what we want to do is be able to take pieces of evidence, combine them and produce intermediate conclusions, and then eventually get some kind of final conclusion that we can compare to the original question we were answering or a claim we're trying to check or something like that. And these are going to combine ideas from logical inference. They're going to be able to do this kind of things that theorem provers would be good at, but ideally also lexical inference, be able to make kind of, understand paraphrase relations and things like that, that NLP models are really good at now. And so this approach kind of lives on a continuum between kind of fully end-to-end approaches like, type it into GPT-3 and see what GPT-3 spits out, and kind of the left side here, which is a lot more constrained in terms of the types of reasoning it can do. So why is this a good idea? I mean, I think that language is probably the best broad coverage semantic representation that we have, in the sense that it's the one that we use every day, and anything else that you try to define on top of it is naturally going to have some kind of restrictions, even as it makes certain things clearer. It's flexible. We can interface with pre-trained models, common sense knowledge bases, Wikipedia, all sorts of resources that are in text without having to convert them to some kind of semantic representation. And finally, it gives us reasoning chains that can be interpreted. So at the top of the slide here, I've shown what this entailment example would look like if we tried to build a little natural language proof of it. And we can do this and understand it without needing to know lambda calculus or something like that. Okay, but obviously, how do we make this all work? Well, there's going to be a lot of pieces that are needed, and one big one is the right data and the right kind of approach to make sure that our models are doing this reasoning correctly. So today I'm going to talk about a couple of different projects in this general vein. So I'm going to start by talking about some work on verifying answers from QA models using textual entailment systems. Then I'm going to talk about, come back to this idea of building these natural language proofs and talk about, sort of line of work there. And I'll conclude by talking a little bit about some new text generation methods that we've been exploring that I think are going to be important for informing that direction. Okay, so the first piece of work I want to talk about is some work led by my student Jifan Chen, joint with Unsel Choi, that was presented at EMNLP Findings last year, about verifying answers to QA systems. And before I get into that, let me just mention that after each of these big chunks, I'm going to pause for questions there. You can also feel free to enter questions or interrupt me along the way. I'm happy to take them. Okay, so the idea behind verifying reading comprehension is the following. We're going to assume that we have some base QA model that can be whatever you want, some kind of model with a latent reasoning process. But when we get the answer from it, we want to check that answer. We want to classify whether or not it's correct. Why do we want to do this? Well, there's some different things that this enables. It can help us deal better with unanswerable questions, or it can improve confidence in our model. Like if we're able to kind of reject some questions as too hard, maybe having a really good notion of how justified this answer is lets us kind of reject ones that we're less likely to get correct. Or we can do things like validate presuppositions in the question that we've seen. Okay, so the idea that we're using is going to be sort of simple conceptually. First, we're going to take the question and the answer, and we are going to feed them through a question to statement conversion module. So this has been explored in the past with rule-based techniques. There is a paper from Dembski et al. In 2018 that used some learning-based methods for it. We trained a T5 3 billion model on their data set to basically plug the answer into the question and get a declarative statement. Okay, then we have the context that the QA model answered the question from. So it went into Wikipedia, it grabbed the answer from somewhere. What was that sentence? So we take that and we feed that through a module called decontextualization. So this was some work that Unseld did at Google before joining UT. And what that system does is it allows you to take a sentence that has things like pronouns in it, and you can replace those with what they actually refer to and then make the sentence stand on its own. So we've got a standalone sentence from the context now, and we've got a declarative statement as a hypothesis, and now we can plug these into an NLI model. And if the context truly answers the question, then it should be the case that the context entails the kind of produced statement under the hypothesis. And in this case, it does not. It turns out that the model is kind of right for the wrong reasons, but there's nothing about who's the bad guy here. All right, so let me just kind of, show the whole pipeline. So we've got a base QA system that gives us an answer. We feed that output into this verifier. The verifier was the piece that we've just seen that combines this question to statement to conversion and this decontextualization piece along with an NLI model to give a competence score. So it doesn't just make a classification decision, but it gives a competence score in it. So this involves kind of natural language reasoning, I think, because we're taking these statements and this context and manipulating them in these certain ways. So what are the kinds of things we can do with this model? Well, we can take a system that was trained on Squad 1.1, which is going to answer every question, and we can run it on Squad 2, which has some questions that are unanswerable. And then we can say, all right, is our verifier able to reject the answers to the unanswerable questions? Basically when the model returned an answer and it shouldn't have, can our verifier spot that? So it's just an experiment to kind of see what the capabilities of this are. And the results we think are pretty encouraging. So it gets around 80% accuracy at both kind of rejecting unanswerable questions and also accepting questions that are answered. And so, in some cases, it's kind of correctly rejecting wrong answers. In some cases, it's not able to fully verify an answer that's correct, but maybe that was still the right thing to do. We're going to see some examples of that later. But I think the cool thing about this isn't a like end-to-end pre-trained model or anything. This is kind of taking these off-the-shelf components and saying, okay, we can assemble these different pieces to do the kind of reasoning that we need in order to reject unanswerable questions here. So what this kind of shows is the flexibility of representing everything in natural language, right? We're able to take this reshaped question and context and feed them into a pre-existing system, an MNLI trained NLI model, because we have these single sentence premises and we have a lot of pre-existing tools that can do reasoning on those. So the other evaluation setting, the one that we focused most on in the paper, was a selective QA setting, where we looked at taking a model trained on natural questions, that data set I mentioned earlier, and generalizing it to 4 different out-of-domain settings. So what we have here is a plot where on the x-axis we have the coverage. That's the fraction of questions that the model is answering. We're saying, okay, the model's allowed to answer only 10% of the questions. Give us the 10% of questions you think are, you're most likely to get right. And so this orange line here is using just the base QA model's posteriors as confidence values. So the QA model spits out some probability associated with the span it extracts, and we can rank all the questions by that and then return the most likely ones. So it turns out that when we use our verifier, we're able to be significantly more reliable at the same coverage level. So at 10% coverage, for example, we go from around 85 F1 to about 90 F1. And this is the model that I've described here with one twist, which is that we train this verifier on both MNLI and also a converted version of natural questions called NQNLI. But note that all of our target settings here are basically out of domain anyway. So this isn't really, this isn't cheating or using anything that the base QA model hasn't seen. Okay, so beyond just that kind of quantitative performance, I think we can actually learn a little bit more by looking at the errors and kind of understanding what this system does. So one lesson we learned was that these kind of manipulations in natural language, like this question answer conversion and decontextualization, are like, these systems are really reliable now. So Jifan, when he did this project, had just come back from an internship at Google. So he was all like chomping at the bit to use the biggest, best pre-trained models. And I was like, do we really need 3 billion parameters to rephrase a question and an answer? And it turns out like, yeah, I mean, you actually do get better performance by going to such big models, and then they work really reliably. So most of the errors here, as you would expect, are from that entailment judgment. But I think the interesting part is that sometimes the entailment model is right. So here's an example of what that looks like. So the QA model proposed as an answer John von Neumann to the question, who developed the central processing unit, CPU? So here's the reformulated version of that. And then here was the context the model answered that from, or the model extracted the answer from. On June 30th, 1945, before ENIAC was made, mathematician John von Neumann distributed the paper titled First Draft of a Report on the EDVAC, blah, 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 stored program computer. So John von Neumann's indicated as the answer here, but the NLI model says, no, there's not enough evidence to determine this. And when we've manipulated the example in this way, we can really examine the kind of assumptions that go into the QA data set. I mean, I think that, first of all, there's some debate about who invented the CPU. Again, you can kind of Google and go down a rabbit hole if you want. But I think it's the nice thing about this approach is that we can really say, is this evidence kind of sufficient to validate the answer and kind of hold it to this high evidentiary standard? So the kind of last thing I want to say about this thread is I want to contrast it with some of the earlier work that we did on building on kind of trying to do the same thing, but with more structured representations. So this is from Jifan's NACL paper last year, where we build graphs over both the question and also the answer context with a combination of semantic role labeling and coreference resolution. And then we treat the QA process as a graph alignment using BERT. And I think this model is really cool and has some really nice advantages, which is that it gives you this kind of explainable alignment structure, and it tells you like exactly kind of why this answer was returned instead of another answer. So I think there's some cool aspects of this, but we found that this was hard to parse into. The tools were actually less reliable than the natural language manipulation we were doing with T5 3 billion in the more recent project. And it was hard to represent all the semantics we needed. I mean, it was like, what do these graphs really mean? Do we need labeled edges? You know, there was all this kind of work, kind of retreading development of semantic formalisms for this problem, which you just totally avoid if you do stuff in natural language. So I think this is also great work that I'm kind of excited about, but you know, I just want to kind of contrast it conceptually with what we've been doing more recently. And so the kind of takeaways from this part, I think, are that using these models to manipulate language, we can use NLI to check answers in QA. And this can kind of let us audit both our models and our data sets. So we can do things like try to, you know, put in a verifier to make a sort of production model more reliable, but we can also challenge the assumptions in our data set, say, is there really enough evidence for us to say this is the answer, or are we teaching the model to kind of guess at things? So that's kind of the story with that. And so I'm happy to take any questions. I'll pause briefly here before going on.
Yeah, actually I have one question, Greg. So let's say when you use an AI model to do answer verification, you basically treat the reference text of a question answering process as the premise. But what if the premise is very long?
Yeah, so I glossed over it. Yeah, so there have been a couple other pieces of work by Mishra et al. And In et al. Who have looked at basically saying, okay, well, why can't we just have the whole document be the premise? And I think, so first of all, in general, there might be cases where you need a couple of sentences as the premise. And I think that can still basically work with this method. But why not do the whole document as the premise? So I think there's sort of a problem there where if you throw me the whole Wikipedia article on like, I don't know, Austin, Texas, like to say if some statement is entailed by that Wikipedia article is like really, really hard because you have to combine all these things and reason. Like, I think we need a slightly more restricted context. So I think there's something in the middle where, you know, I would imagine like kind of 2 or 3 sentences being the right amount in a lot of cases. But yeah, here we were just doing 1 sentence, and that's definitely a kind of restriction. Like there's some questions that just don't work well because you need more than that.
I see. Yeah, thanks. Okay, I see there's another question from the chat. So how do we decide the input premise in this case?
Yeah, so the premise, basically yeah, so basically this base QA model that returns an answer, we've been looking at this in the case of extractive QA. So it extracts it from a span. And so the sentence that I've picked out at the top of the slide here, that's the span, Ted Danson, that the model picked, that the first QA model picked the answer from. And then we just take the sentence that contains it. So you could take, yeah, you could take sort of sentences on either side, but you get it from the base model.
Okay, so that means if, let's say if the base model is not giving the correct span, then the premise will not be the right one.
Yeah, I mean, we're kind of asking both, is the base model right? And also, is it right for the right reasons? Like, did it pick that span from a sentence that actually justifies it? So also, if you, like, let's say you were doing some kind of closed book generative thing, you know, like this approach would not work because you would need to then go look up some other evidence. Like this only makes sense in the case of open book models.
I see. Thanks.
Okay, should I move on?
Oh, there's another question. So in Bayesian model, do we add additional algorithms for accuracy then?
I think it. So the base model here, I mean, is the, I'm assuming that's what that refers to. That's the kind of standard input, the sort of standard QA model that we're running that just returns some kind of answer. So this is an approach, like this verifier can improve the accuracy of that original model. I mean, it also can use whatever kind of black box QA model you want. So I mean, if you can do other kinds of modifications or place extra constraints on where it gets the context from. Yeah, I'm not sure if I answered the question fully, but
yeah, I think yeah. So the chat verified the answer.
Yep.
Good answer. Yeah, thanks. Let's probably move on.
Okay. Yeah, so that's kind of one instance of this natural language manipulation. So I want to talk about another line here. In a vein we call natural language deduction. So this is work led by my student Kai Bostrom, along with Lucy Zhao, Zane Sprague, Swarat Chowdhury, and one paper was presented at EMNLP, and we have another paper in preparation right now. So the general idea here is kind of coming back to that initial goal of like, let's kind of construct this proof tree of a statement. And so if we have two statements like apples belong to the tree fruits and the produce of fruit trees can be eaten, we define an operation called natural language deduction, which is that we should be able to take these two statements and generate a valid conclusion, or more generally, place a distribution over the set of valid conclusions from these statements. So for example, we should be able to feed these two sentences into BART and get as output, apples are edible. So this is the type of thing we're trying to build. And so, it seems like BART should be able to do this. The main question is how we get the right training data. Because it's, it's very hard to find instances of this kind of sort of logical reasoning and text in the wild. So our approach that I'm going to talk about here is about building a data set in an automated way. So we sort of took a semi-synthetic approach to constructing data that turns out to be very useful for doing this task. At the same time, actually also published at EMNLP, there was some work from AI2, which constructed supervised data for it that has some kind of interesting contrast with our approach. But I will say that we have a lot more data, and in their paper, they say that it took 600 hours for the students and researchers on the team of manually constructing this stuff because it was too difficult to do with crowd workers. So I think ultimately we're sort of happy with the approach that we took, and that we didn't spend 600 hours building these kind of examples, but we have a method for kind of generating these sorts of data sets. So let me tell you about how our method works. And it relies on the fact that the inference that we want to get really kind of blends two processes. First, we have logical inference, like things of X have property Z, things of Y are of type X, therefore things of Y have property Z. So that kind of relation I described is kind of independent of the specific lexical content. That's just kind of a general like logical rule that you can apply anywhere. We also have lexical inferences. So for example, on that previous slide in our example, we had the produce of fruit trees can be eaten and apples are edible. Right. So this is the kind of thing that formal semantic representations usually break down on pretty hard, because knowing that these two things are paraphrases or entail each other is tough. So we're going to kind of get the ideas from logical inference by generating some templated data that teaches our model that type of reasoning. And we're going to rely on pre-trained language models to learn the lexical inference, as well as some paraphrastic data augmentation, which it turns out is going to be really important. So what we do is we start from Wikipedia, and we're going to scrape a whole bunch of data conforming to some patterns. Then we're going to manipulate those examples to build inference examples that are going to teach our model what we want it to learn. Okay, so this data generation piece starts with using some Hurst patterns to scrape source sentences. And so here's the kind of thing we get from that. So we run a dependency parser over Wikipedia, and then we look for little parse fragments like this one. So basically plural nouns such as blank do X VP, this VPP $2 thing. And so this will match sentences like the following. The fertile basins, such as the large Thuringian basin, are in intensive use for growing fruits and vegetables. And so even though it's hard to find these kind of nice 3-sentence examples like we've been seeing, A, B, implies C, we can find sentences like this that actually encapsulate that same kind of reasoning. We have a rule-based template kind of paired with this pattern that will then rewrite these sentences to say the fertile basins are in intensive use for growing fruits and vegetables. That's kind of clear from the original sentence. The large Thuringian basin is a fertile basin. That's sort of clear because of this such as Hurst pattern that indicates this hypernymy relationship. And then we can derive the conclusion here in the same way. So we've kind of extracted this instance from Wikipedia here, and now we can train our model on it. So the third step that I mentioned before was this paraphrasing. And so if you train a model over just this kind of rule-based data, you're only going to learn to do these very surface level manipulations. So what we do is we feed the premises through an automatic paraphrasing model. And this is going to give us source sentences that now look like the following. Growing fruits and vegetables requires a lot of fertile basins. Okay, not so good. The Thuringian Basin is fertile. That's fine. I mean, assuming the Thuringian Basin and the large Thuringian Basin are the same thing. So the nice thing here is that this is data augmentation. And so it adds a little bit of noise. But generally what it does is it makes the model robust to lexical variation. And we find that it's still able to kind of capture the essence of these things and generate correct conclusions. So one reason that we only did it to the premises is you sort of corrupt the input, but you keep the output clean. And so it learns this kind of denoising effect. Okay, so that was our process. So we scraped a bunch of data. And the scraping actually, we find relatively few examples of this on Wikipedia compared to what you might think of. So the patterns that we have only match around 40,000 sentences, which is not a large fraction of Wikipedia. But once you actually expand this with the paraphrasing model, it ends up being around 100,000 examples, which is plenty to learn the kinds of operations that we want. So the kinds of things then that our model can do, so we train a BART model on this. We have a sentence pair like this. Doctors use medical tests to diagnose diseases and guide treatment. Some of the most common diagnostic procedures include blood count and other multi-factor panels. This is taken from that AI2 data set I mentioned earlier. So one baseline that we compared to was just training BART on MNLI. So take the premise as input and generate the hypothesis that for entailed cases. And that should learn to generate entailed statements based on premises. In this case, the model just repeats the first premise. It doesn't know how to kind of put these two things together. Our pattern-only model, which doesn't use the paraphrastic augmentation, also does the same thing. It just repeats the first premise. But the full model that we build is able to generate the following. Doctors use blood counts and other multi-factor panels, so it kind of grabbed that from the second sentence, to diagnose diseases and guide treatment. So it recognizes that these diagnostic procedures are part of the medical tests that are diagnosing things, right? And it sort of correctly unifies this across the two sentences in a way that's fairly non-trivial. I mean, again, kind of thinking about formal semantic representations of this, it's hard to recognize that there's really a kind of inference that can be made there. All right, and just to show one other example, sort of, again, these are a little bit cherry picked, but humans changing an ecosystem usually has a negative impact on an ecosystem. Humans building homes in an ecosystem causes that ecosystem to change. The system's correctly able to determine that, okay, causing something and, that something being a negative impact means that humans building homes usually has a negative impact on an ecosystem. So we evaluated a little more rigorously on two data sets. The first is this question answering by sentence composition data set from Tushar-Kott et al. From AI2. And what we did was we did human evaluation of these generated premises. And basically the green bar here means it's good. The blue bar is it's good, but basically there might be some minor errors. And the gray is that it was repeated. And the orange is just kind of it generated something bad or invalid or kind of incorrect reasoning. And so the cool thing here was that our model on our semi-synthetic kind of scraped data was able to basically match the performance of entailment bank BART and cask BART, which are models that are trained on, again, this kind of labeled supervised data. So we're able to do basically as well as these techniques without using any of the data that took 600 hours to label. And the thing I think is really cool, which we'll come back to in just 2 minutes, is that when the model fails, it usually just repeats the first premise, which is at least okay. That's still a valid inference, right? I mean, it's a vacuous inference. It's just repeating stuff, but it's not wrong. It's not just like making up facts. So we have some results on the entailment bank data set as well, where again, the kind of conclusion is that we can basically do as well as their techniques. We don't cover all of the reasoning types in this data set, although we actually do pretty well, given that theoretically, there should be big chunks of the data set that we can't handle. Okay, so let me zoom out. So we talked about how to take these pieces of evidence and and kind of build and kind of generate these deduced statements from them, right? So our goal that I outlined at the beginning was to be able to take some evidence, prove this whole kind of chain of statements, and then eventually justify our claim or justify the answer to a question or whatever. So beyond just the model that we've got here, there's also a search problem. We need to be able to apply these kind of operations, this deduction operation, to get the conclusions that we need. And this is tough because what we're doing is we're generating intermediate statements in natural language. And this is a very large state space that we're exploring if it's the space of kind of all true statements. So we have some kind of initial progress here, which I'll just kind of briefly discuss, where we've been looking at different search heuristics for prioritizing this search. So here's an example of the kind of thing we want to be able to do. So we have 3 evidence sentences here. This is a kind of artificially simple example for the slide. Paper is recyclable. Recyclable means old material can be converted into new material. Cardstock is a type of paper. And then we have a hypothesis, old cardstock can be turned into new cardstock. So we want to figure out how do we combine these sentences with our deduction model to prove this hypothesis. So, one thing that we can recognize is that that model, like I said, fails in an interesting way, which is that it usually generates just the first premise, whatever you feed into it first again. So if you feed in S2 and S3 here, it's pretty hard to generate a kind of non-trivial deduced inference from these because there's not a lot that can be combined between these 2 sentences. So the model has a very high probability of just copying the first thing, and that can be a heuristic that we use to prioritize the search. So we can recognize that, okay, 2 of these statements or 2 of these pairs, if you combine them together, there's something nice you can generate, but the third one, not so much. We've also been exploring a little bit with a learned heuristic that looks at a pair of sentences and also the hypothesis itself. This is a trained model that says how likely are these hypotheses going, or how likely are these sentences going to be? How likely is it that these sentences are kind of on the road to proving that hypothesis? It's a little bit of a sort of tricky notion, but we train it on, we actually do need the supervised entailment bank data to train that. Okay, so then at the end of the day, what the system's able to do is it's able to prioritize, okay, first I should combine these 2 statements and figure out that cardstock is recyclable. Then I combine that generated statement with recyclable means old material, blah, blah, blah. And we recognize that old cardstock can be converted into new cardstock. And then finally, we bring back that NLI model we were talking about before to judge the equivalence between these 2 things. So notice that the hypothesis was old cardstock can be turned into new cardstock, not converted. And so an NLI model can help us kind of bridge to that hypothesis and say, yeah, okay, we proved something basically the same. Okay, so that's basically the system that we've got. It's able to take these sentences, combine them together, and do that repeatedly in this guided search to try to prove or disprove a hypothesis. So here's our kind of initial results on this, which is that we've been looking at sets of 25 premises with a hypothesis that's potentially true, and usually takes maybe 2 or 3 steps of inference here to get to. And our goal is to classify the hypothesis as true or false and build this kind of tree of entailed statements. So the baseline that we compare to in green here is a pure end-to-end model. So this was from the entailment bank paper, where what they do is they just try to straight up generate a whole bunch of statements, and then at the end generate the hypothesis, and we look at the probability they assign to those generation decisions. The problem is that this model is very easily misled into generating things that should not be true. It'll tend to just kind of generate the hypothesis, whether or not it actually follows from the evidence. So this model is not very good at separating correct from incorrect things. So what we're showing on the right in the graph here is a precision recall curve. So the orange model, which is our best model, uses this goal conditioned heuristic, and it's able to prove about 80% of the true statements with nearly 100% precision. So it basically proves correct stuff without proving any of the kind of distractor or false statements. And then, at a certain point, it sort of loses its ability to recall, probably because there's errors in the individual steps. We've looked at sort of where it goes wrong, and sometimes it just kind of sticks sentences together in ways that aren't quite right. But basically, this goal-driven search is able to do a pretty good job at following these sorts of reasoning patterns and building these proof trees and explanations for what we're trying to show here. So this brings me to the end of my second part, where I think the takeaways are that we were able to build this model to do this kind of logical reasoning without a lot of human training signal, and no kind of formal semantics or logical forms in sight, really. There's a little bit of kind of dependency patterns used in constructing the data, but otherwise it's kind of everything's in natural language. These models are flexible. They're able to adapt to these different data sets, fairly fluidly. And when we integrate these into this multi-step system, there's some kind of promising results. So, we think that kind of how we structure that is really going to be an important tool going forward. So I'm gonna just mention two applications that we want to use for this, and then I'll pause for questions for this part. One is just, this is sort of future work, but coming back to the idea of fact checking. A lot of claims that we might want to check are complex and have multiple parts. So there's some previous work by Angela Fan et al. Looking at kind of generating sub-questions for these and retrieving evidence. One thing that we're looking at doing, which they did not do, is take those pieces of retrieved evidence, use these deduction models to combine them together, and then prove or disprove various parts of the claim. So that, I think, is a kind of exciting direction towards more explainable fact checking. And another thing we've been looking at is entity-centric reasoning. So if we have, we collected a data set at the NeurIPS data set and benchmark track this past year, led by my student Yasumasa, joint with Michael and Unsel from UT, where we looked at sort of made up claims about real world entities, or in this case, real fictional entities, I guess, where if you say Harry Potter can teach classes on how to fly on a broomstick, you are sort of combining some entity knowledge about Harry Potter with the knowledge that, even though you haven't seen this before, that someone who's good at something can probably teach someone else how to do it, right? So these are claims that people are very good at writing down and we typically agree on, but we're not really great at doing reasoning about these yet. And I think having the kinds of deductive explanations of these things would be really cool, although we don't know how to do that yet. So that's definitely future work. All right, let me pause there at the end of this section and take any questions. Okay, I see one here. Stop words can change the sentence meaning. So does Pegasus take care of that while paraphrasing, or do we exclude it entirely? Is Pegasus a paraphraser, or Pegasus is a paraphraser? Yeah, that's a good question. Let me come back. Yeah, here's where the paraphrasing was happening. So, I mean, we don't really have an explicit control. I think typically it doesn't paraphrase something that's like not a question into a question or vice versa. So usually stuff remains as declarative statements. You do get stuff that's screwed up, like requires a lot of fertile basins. It sort of like has the right idea where it's like, well, fertile basins help you grow stuff, but growing does not require a fertile basin, right? And the grammaticality is kind of weird. And I think, basically the answer is, it's a pre-trained model. It works reasonably well. And so it doesn't have kind of big mistakes, but it can definitely garble stop words. It can definitely kind of butcher the input a little bit. Yeah, I don't know. Anything else for now? Any other questions? Okay, well, let me maybe go through my last section of the talk, and then we'll probably have time for a few questions at the end. So Okay, yeah. So the last thing I want to mention just kind of briefly is some improvements to generation. This is a project led by my student Jiacheng Xu. And basically the kind of lead in I'll say here is that for this kind of natural language deduction, one of the pieces that we kind of glossed over was how do you actually generate the right deduced statement? So in this case, going back to the changing an ecosystem has a negative impact on both the ecosystem and the organisms in that ecosystem. So we could generate sentences that talk about the negative impact on the ecosystem or on the organisms, right? So there's a lot of correct generations, and we'd like to have systems that just kind of give you lots of generation options. So I'll talk a little bit about some work we've been doing on diverse generation. We're going to present it in the context of summarization, just because that's what we've been kind of working on more, but it is something that I think we want to apply to this kind of deduction and reasoning as well. Okay, so this is the example that Jiacheng likes, is summarizing the blog post about BART using a BART model, which I think is kind of cheeky. So basically, if you feed this blog post into a BART large XSUM model, you get a bunch of summaries that come out of Beam search. And so the top summary is a pre-training model for natural language translation has been proposed by a team of researchers at the Massachusetts Institute of Technology. All right, and you get several options here. Now, the first thing you might notice is that all of these options have the same prefix. The second thing, if you're familiar with BART, is that it was not proposed by people from MIT, it was people from Facebook or Meta. And so Beam search gives a lot of similar answers that are all wrong in this case. And instead, what if we could see a whole bunch of different summaries? So we're going to talk about some issues with Beam search that prevent getting more diverse outputs and then how to fix them. So the first problem is that Beam search is very redundant. If we have things like a new model and a novel model in the Beam, these can then lead to just sort of clogging up the Beam with sort of ambiguities that don't really matter all that much, right? Like new and novel, basically synonyms. We don't need to necessarily encode all that lexical variation. They could be very important in certain tasks, but in general, a lot of times you get stuff that just ends up being very similar. So the first thing that we do is we look at rethinking the structure of the Beam, and instead of kind of storing complete candidates, we instead store pointers to compacted lattices of generation candidates. So in this case, when I draw a box here with the word model in it, that's actually going to be a pointer to a lattice over on the left, which encodes 3 different summaries, all ending in model. A new model, a novel model, a pre-trained model. So we freed up some space now to include some other more different generation candidates as well. The tricky thing is that now we're making an assumption, and the assumption is that all of these things ending in model can be treated the same. So in the good old days of phrase-based machine translation, this was something that you could do. It's called hypothesis recombination, because when you're using n-gram language models, if the last couple words are the same, the language model isn't going to care about some changes that happened way long ago. However, neural generation models are going to look at the entire context, and the distributions of next stuff are not going to be the same. So fundamentally, what we're doing is an approximation, but we make the same kind of approximation that was used in phrase-based MT. We look at if the last few tokens were the same and if the lengths are roughly the same. And then what we say is that, okay, if we have hypotheses like a new model for natural language or a novel pre-training model for natural language, these end in the same suffix. Let's just kind of join them up and treat them as the same thing in this lattice search procedure. And so we're assuming that the distribution over what the generation model produces afterwards is going to be the same for each of these two generation candidates. And we found that this assumption was kind of generally true. I'm not going to go into the details on this much, but this kind of procedure basically works okay. So this kind of recombination was explored by Zhisong Zhang et al. In some earlier work at EMNLP 2018. We kind of took a new look at their criteria and evaluated it in the context of some different pre-trained models and found that it actually kind of still works pretty well. The second problem with Beam search is that you spend a lot of time exploring hypotheses that end up getting discarded because you're trying to find the one best and not get diverse options. So in beam search, as your kind of search goes along, you'll start to lose stuff from earlier in the search. They'll kind of fall off the beam, right? And then at the end, everything is a pre-training model for blah, blah, blah. So that means that you're spending a lot of time and a lot of GPU cycles expanding and computing the distribution of next words for nodes in the search graph that end up never getting used. And so in this case, even after just these few time steps of search, only 5 out of 12 states that we checked in the first 3 beams actually got used in the end. So we're like wasting a lot of computation if what we care about is diversity, right? We're checking a lot of states and then saying, oh, it's like not quite good enough, not quite as good as our one best here. Whereas in reality, all of these would lead to fine generation outputs. So what we did was we restructured the search so that we want every explored state to be on a finished path. And the idea here kind of draws on ideas both from best first search and also depth first search. So what we do is we start expanding nodes and exploring the search graph here. And we expand in descending order of model score. So basically we're looking at the most likely things first. But when we get to a point where, we would have started kind of generating along a different branch, we instead say, no, okay, you have to go all the way to the end of sentence token from this prefix that you've got so far. That way we'll guarantee that there is a finished path there. And then once we've generated that, we'll kind of come back and start looking at this branch, a pre-training model. And this actually interacts really favorably with the recombination stuff because now we keep generating and then we're going to say, oh, okay, actually this n-gram kind of matches the one up here and we can merge these things. So I went through that a little fast because I want to leave some time for questions, but basically the output is that we get this packed lattice of summaries. And it's able to encode a bunch of different summaries in a relatively compact way. So rather than having a bunch of different candidates in a beam, we can say, okay, this is an article about Apple misleading Australian consumers over the new iPad, but we managed to encode 8 different summaries here, misleading consumers over the iPad, misleading customers about its new iPad, all in this kind of efficient lattice structure. So basically our experiments were trying to look at whether we get a lot of outputs, which is what we want, and also high quality outputs. So what we found is that our kind of main variant of the method was able to get a relatively high Oracle Rouge value compared to baseline. So it's able to produce a summary or encode a summary that's kind of a bit closer to the gold than what the other methods are able to do, and also encode a large number of absolute paths in this lattice. And then we have a relaxed version of this method that encodes sort of even more paths with the sort of caveat that it has a little bit of a lower quality. There's some kind of grammatical errors that get introduced along the way. And so it's sort of not perfect. So we're interested in kind of figuring out more if there's more that can be done with these merging heuristics to both get lots of good generation candidates while also kind of maintaining the highest quality possible. So to kind of zoom out and conclude, and then I'll wrap up the whole talk and take some questions. I think that what this shows is that our generation models already encode lots of good options. It would be great if we just had a way to access all of them rather than kind of throwing out most of them except for the very top few. And so this opens the door for things like re-ranking or users kind of dynamically controlling and correcting the system on the fly to kind of pick a different generation option. I think there's a lot of exciting applications for this kind of stuff, and kind of thinking about it in the context of that deductive proof engine that we saw. I think that we are kind of closer than ever to actually being able to search over these natural language proofs with some of these new generation techniques. And ultimately, I think that it's kind of this whole direction is kind of betting on the right horse in some sense, where as generation models get better and better, we're going to see all of these kinds of natural language manipulations that I've talked about today, like these question conversion models, these you know, decontextualization, these deduction models, all this stuff is going to get better when, you know, GPT-4 and T6 and whatever come out. I know the 5 isn't a 5, but anyway, yeah. So let me just kind of wrap up there, which is that I'm excited about the capability of these, of kind of doing complex reasoning in natural language. Natural language is a good vehicle for doing this. And hopefully what I've shown you today convinces you that there's some potential in taking these ideas and kind of, marrying them with formal logic, and kind of further improvements are going to just lead to sort of lift all the boats and enable us to do even better reasoning for domains from common sense to this kind of science question answering to fact checking to all kinds of things. So thanks everyone for your attention today. I want to thank all of my collaborators and colleagues at UT Austin who helped make this work possible, as well as my funding sources. So thanks.
Yeah, thanks, Greg, for the very exciting talk. And I totally agree that natural language is the right vehicle for reasoning. Yeah, I guess there are already some questions in the chat. I think the top question is regarding the second section, actually.
Yeah, I saw it. I saw it pop up, and yeah. So let me come back to that. Is this sort of encyclopedia style of wiki articles helpful for structuring training data? Yeah, so that's a good question. Basically, is the reason that this kind of procedure works? I mean, let me see if I'm understanding the question correctly. I think it's that is the reason this works because Wikipedia is written in a certain style. I would say like it's a little bit hard to answer that question because we didn't look at what these patterns would match on other data sets. I do think there's a I mean, Wikipedia obviously has certain kinds of inferences very prominently, but there was also some stuff that we couldn't find a lot of. Like we were hoping to find a pattern that would really kind of allow us to capture more temporal reasoning or certain things around quantification. And we weren't really able to find good patterns for that. So I'd say yes and no. Like I think probably the reason that some of this stuff that did works is because of how Wikipedia is, but it also prevented us from getting other things working. So yeah.
Okay, any other questions from the audience?
I'm curious. Hi, this was a very interesting talk. Thank you. I'm curious whether your natural language deduction model can handle any form of negation, where sort of very small differences in surface structure, lead to completely different meaning.
Yeah, that's a great question. So one of the other, like basically the sort of pattern that we're talking about here largely was this like substitution pattern where, you're kind of unifying across this shared variable between these two sentences, essentially. It is able to handle negation. So in particular, we also explored the ability to do reasoning about contraposition. And one of the, and we also found that the model was at least decent. I mean, not perfect, but decent at handling things like inedible, where the negation gets kind of wrapped up. It sort of gets transplanted from an explicit not into the, into an adjective or something itself. So yeah, I mean, obviously, like you start to get into these cases where, so I guess let me put it another way. Typically where this breaks down is where there's a kind of like implicit like restrictiveness to one of the predicates that's kind of not obvious. Or you just have kind of lexical items that that it doesn't really know how to deal with or reason about. It's kind of vague. I don't have good errors to show off the top of my head, but yeah. You're muted.
Sorry. One more quick question. That was about the, sort of controlling the search. And, so in a traditional inference system, you use all kinds of indexing to sort of find the right rules that sort of might lead you to an answer. And I wasn't sure I fully understood what you were doing, but I mean, you could do some sort of soft indexing, I assume, where you sort of, for every particular statement, you index others that might be potentially relevant to that. Are you doing something like that, or is it a different approach?
No, I mean, right now, what we have are 25 premises. So we're able to just kind of check all the pairs and it doesn't break the bank. I mean, and I think a lot, like you can get pretty far with kind of IR to just like restrict the set that you have. So we don't have a real good setting yet where it's like you need to be able to handle like hundreds or thousands of potentially relevant things that you can't kind of pre-screen. But you're absolutely right that you know, I think at the end of the day, we're going to need more efficient techniques to deal with this. There's this paper called NL Prologue from maybe a few years ago. I think Tim Rocktaschel is one of the authors, where they kind of build a soft version of Prologue and they apply it to some of this multi-hop reasoning stuff. And that has some cool ideas about kind of soft backward chaining and things like that. That are also kind of relevant. So one of the things that we've been thinking about also is like, can you build like a plan in some way using like one kind of reasoning system and then flesh that out in natural language here? But yeah, so there's a lot of space to explore things, and we're not going to have time to do it all. Oh, I see a question. How about handling every or all? Yeah, actually, so handling that works okay. Handling some or like few or things like that, like those are the kind of quantifiers where I think we would like, you know, the system tends to break down more. I think we need data that's kind of specifically targeted towards those kind of inferences, and like, I don't know, quantification is hard. I don't have I don't have anything else to say.
Yeah, I also agree that when the reason is regarding quantification or temporal reasoning or any kind of aggregation, it's actually going to be very difficult for natural language inference. Yeah. Yeah. Any other questions? Although we are already at the time of 12. So I guess if there's no question, let's follow up with the one-on-one discussions. And I do think, you know, many of us will have lots of questions over there as well. Okay, thanks, Greg, again for this very inspiring talk of those, you know, very exciting works from your group. We do have learned a lot, I guess. And
okay, well, thank you, and thanks for having me, and thanks for attending, everyone.
see you soon. Bye.